All right, here we go. So today, we're starting Chapter 3, and we're going to be dealing with solving quadratics. I talked about this a few days ago, about how Chapter 2 is really all about building quadratics, and Chapter 3 is all about working with them and solving them and that sort of thing. So the difference is, in Chapter 2, the result of what you were doing was an equation. With what we're doing today, for example, the result is going to be a number. Okay, you're going to use a quadratic equation that's given to you, and you're going to try and figure out the solution. Now, this is the kind of math through algebra and geometry that you guys are a little more used to doing. Okay, solving equations should sound familiar. You've done a bit of it up to this point. Okay, so we're going to be solving quadratics specifically. Okay, so we're going to be looking at three different ways to do that. Solving quadratic equations by graphing, which you can use your calculator to do. Using square roots, so like square rooting both sides of an equation to try and solve. And then the third one, factoring, by using this thing called the zero product property that you've probably seen before, but it's been a little while, I would guess. So we'll refresh you on that. Okay? So, but in general, what are we doing when we solve a quadratic? Well, what we want is to know what values of x will make ax squared plus bx plus c, so some quadratic, equal to 0. So when we solve a quadratic, or we're finding a solution to a quadratic, that's what we're doing. Trying to figure out what number, if I plug it in for x, will make the whole thing turn to 0. Okay? So, first method we talked about that we're going to do, graphing. All right, so let me draw you a quick little picture here. So let's say we got some parabola that looks like that. Here's the y-axis, x-axis. So if what we're trying to do is to find x values that will make the equation equal to 0, where are we going to look on the graph then to try and find these solutions? If that's the method we're going to use, what are we looking for on there? The x-axis, right. Okay, we want to know what are the values of x that make the equation, or y, 0. So where on a graph is y equal to 0? Anywhere along the x-axis. Okay, so our points of interest then are going to be where that function, or that quadratic in this case, is hitting that x-axis. Okay. So those x-intercepts are solutions to a quadratic, because at those places y equals 0. That's the only reason we're interested in those. Because if this is our goal, is to make the thing equal to 0, well then the x-intercepts are going to do it. That's where y is 0. So, what equation are you thinking of? The quadratic formula? Is that what you're thinking of?
Where we take the x-intercepts and we plug them into the equation.
Oh, intercept form?
Yeah.
Is that what you're thinking of? Yeah, we're going to talk about that in just a minute. This is very closely related to that.
Why don't we just use them?
Because they're not always written in intercept form. If they're written in intercept form, yeah, it's easy. You can just use the equation and boom, boom, there are your solutions. But it's not always written that way, so you can't. Okay, could be vertex form, could be standard form. Then you got to try some other stuff. So, all right, so let's try this once. Like I said, this stuff you can use your calculator for. So, all right, so let's go ahead and punch that one in. x squared minus x minus 6. And like we said, I'm putting it equal to 0 again because that's what we're interested in, right? But on your calculator, you don't need to write the equal 0. You just put it in your y equals and take a look. All right, so everybody knows how to get here, right? Okay, then let's just type that in. X squared minus x minus 6. And before you hit graph, your window might be something different from the last time that you used it, okay? And you might not be able to see the parabola in there based on whatever it was you were working on last time. So just as kind of a nice, safe place to start, if you go to zoom and down to number 6, Z standard, that's a standard window, which is negative 10 to 10 on the x and negative 10 to 10 on the y. So if we go ahead and hit enter on that, usually you're going to be able to see it when you do the standard window. Okay? Question?
Mine says error.
What kind of error does it say?
Invalid dimension.
Did you do the zoom standard?
Did that too.
Oh, okay. Go back to y equals. Where it says plot 1, plot 2, and plot 3, are any of those highlighted?
Plot 1.
Yep. Unhighlight it. It's trying to do a scatter plot and a graph at the same time, and it doesn't understand which one you want.
How do you go up to it?
You just go up to it and hit enter. See, now mine's highlighted, so if I want to get rid of it,
Mine was highlighted.
you go up, hit enter, that turns it off.
And it still gave me the graph.
Sometimes it does. If the scatter plot or whatever you had in there is on the same window that you were graphing the parabola, it's okay. But if it can't put the data together somehow, then it's going to be confused. You go to zoom and then Z standard, number 6. Okay, and that gives you the nice standard window. Or like I was saying, you like 99% of the time, a standard window for what we're doing in here is going to show you what you need. Okay, maybe you need to zoom in just a little bit to see it clearly, but most of the time it's okay. So where would you say the x-intercepts are on this graph just by looking at that thing?
2 and 3. Negative 2 and 3.
Yeah, there we go. So negative 2, positive 3. All right, well, let's write those down real quick. Okay, now, do we know for sure that those are the two intercepts? Kind of appeared to be that way, but what if it was like 3.01 or something? We really wouldn't be able to tell. So what can we do to check that those are actually solutions to this equation? Yeah, plug them in. Because remember, they're supposed to make the whole thing equal 0, right? So if we plug them in and it makes it 0, we know we're good. So let's try that once.
How do you know which x?
You try these two numbers. The ones that you found that you think are right, you're going to check those. Both of them. You got to check both of them.
The equation, one of them is going to be squared and one of them is not.
No, not. You do the whole equation with one and the whole equation with the other. All right? So try typing that in your calculator even if you want to. If you don't want to try and do that math in your head. Negative 2 squared minus negative 2 minus 6. Should tell you 0. Okay, that should work. So we've verified then that, yeah, that one is a root. It is a solution to that equation. And then we do the same thing with the 3. 3 squared minus 3 minus 6. Check to see if that comes out to 0. Yeah, Levi? Mm-hmm.
That's what I noticed during my test. When I type in like a negative number, try to square it, it's like wrong.
Yeah, well, actually what you're telling your calculator to do right there is to do 2 squared and then make it negative. So you have to use the parentheses if you're trying to square it with the negative. So does the 3 make it 0 as well? That one works? Okay. So we verified both of them. We're good. That's where those two solutions actually are. If it doesn't work, good.
If you got that just by looking at the calculator.
Right. Mm-hmm.
What happens if it's a weird number?
So if it doesn't come out to like a nice negative 2 or positive 3, what if it is like 3.02 or something like that? Okay. So if this doesn't work, well, let's look at another one where this wouldn't work. How about? Might as well just do that. Because it's a good question, because that does come up. You're not going to see it in your homework today, but it'll come up later, so we might as well talk about it now. How about we do that, but then minus 2. Okay. This one I'm pretty sure is going to give us a not normal answer. Okay, so x squared plus 3x minus 2. Let's see what we get. Okay, yep. Type that one in and take a look. Is that parabola hitting the x-axis at a nice, neat number? Looks like it might be halfway in between a couple of them there. Like maybe the solutions are 1/2 and like negative 3.5 or something. Okay? Now if you want to know for sure where those things are headed, okay, if it's one like this first one where it comes out to a nice integer, go ahead and just plug it in and double check and then you're good. If it doesn't, what I would do first is there's this function on your calculator that will tell you for certain where it is. Uh-huh. You hit, because it would be a lot more work for this one than what it's worth. Because if you can look at it and see, oh, it's probably those two, and then quick check it, it's a lot less work. But if it's not, so then you can go second, trace, and there's this calculate menu. And you want number 2. Okay, intersect is different. Intersect means you have two graphs that are crossing each other somewhere. Intercept is on the axis, and that's actually a 0. We'll talk about that in a minute. There's different names for the same thing. Okay, so second trace takes you here, and then you hit 0, and it's going to ask for a left bound, and you're going to see this little cursor that's blinking on your parabola, and you want to move it just to the left of where you think one of those zeros are, and hit enter. And it'll ask for a right bound, and then you move the little blinky cursor just to the right of where you think it is. Hit enter. And then it'll ask you, do you want me to take a guess in between those two numbers? And you hit enter one more time to say yes.
-2.
And it's negative 3.56.
Can you go back to the y equals? X squared plus 3x minus, oh, I said plus 2.
Should be x squared plus 3x minus 2. Y'all got that? So let me go through it one more time. Second, calc, 0. Go a little to the left of where you think the x-intercept is. Hit enter. And then scoot it a little bit to the right of where you think that x-intercept is. Hit enter. Enter again. That one should be at negative 3.56 and some change.
So do you go right above the x-intercept?
Well, think of it more as left and right instead of above and below. But, yeah, technically. So you'd want to be over this way from where it looks like it crosses, and then over there. On the other one, too, your left bound would be down from the 0 then, right? And the right bound would be up because it's to the left and to the right.
3.4. I don't know what I got.
Or do I press enter?
You have to hit enter still.
How come I got -3.5? Once we get to the guess, what do we have to press?
Enter.
That's what I did.
Yeah, that's right. That's the other one. There's 2 of them, right? I only found 1 so far. This one's negative 3.56. The other one's going to be like 0.5 something.
Yeah.
All right, so if I repeat the process, second calc, 0, I got to repeat the process for the other one because there's 2. So if I come over here, my left bound is probably going to be somewhere about right there. Hit enter, and then the right bound would be somewhere over here. And then enter again. And it's about, 0.56 would be the second one. Bless you. Now, for the ones you guys are going to work on your homework, it should be fairly obvious where they are. Okay? But, like I said, later on, we're going to have to do it this way on the graph. So we'll get there. So it's more of kind of a little preview for you. But In any event, we can do this, though. It's negative 3.56. I'm going to round them off, and then 0.56. Okay, so it is doable, but it's not as crucial a thing at this point for you guys. All right, I got one more I want you guys to take a look at with the graphing here, and then we'll be done. If I had x squared plus 4 equals 0. This one you might not even need a calculator for. Think about it for a second. Think about your transformations. X squared, think about what x squared looks like. Hold on. Just a regular x squared is a parabola with its vertex where? At the origin, 0, 0. If I put a plus 4 on it, what am I doing to that parabola? Moving it up 4. So if it started, think about this in your head, visualize it. If I had a parabola that had a vertex at 0, 0, and I moved it up 4, what are the x-intercepts?
0. None.
None. Doesn't have any. Okay? There are some of these where there are no solution. Okay? If there are no x-intercepts, there's no value of x you could possibly put into that thing and make it work. So there's just no solution. No. It's an okay equation. It just happens to be a parabola that doesn't cross the x-axis.
If it's just x squared, there's only one solution, isn't there?
No.
Really?
Sometimes there's two.
But if it's just x squared equals 0,
That's only one solution. Right. That would be one solution. But if I took that x squared, let's say I went minus 4, moved it down,
Going down forward, then you have 2 solutions.
then you have two solutions. Right.
Going down.
Right. Exactly. Uh-huh.
So do you have to have two, like, x-intercepts in order to have the equation work?
Could be one. Like we were just talking about, what if it just was x squared without the plus 4? The vertex, if the vertex is sitting right on the x-axis, because this one's been moved up. It started there, but then we moved it up. So then there's nothing touching the x-axis anymore. So it has no solution whatsoever. Okay, so there are 3 different cases, I guess, for how many solutions you could have. You could have 2, like the first examples we did. There could be none, like this one. Or it could be that the vertex happens to be sitting right on the x-axis, in which case you'd have 1. Okay? We're not done yet. I've only told you the one method out of the 3 I was going to teach you today. Okay. Great, you awake? Yeah? I'm pretty sleepy. All right, so that's using graphing to do it. Okay. This one, again, if we did it on the calculator, it would look something like this, where the vertex would be up at 4. So nothing crossing, no solution. All right. So, all right. The next method, square roots. All right, so the only thing you really need to remember on this one is you need to get the square by itself. It's called isolating the square. Okay, so give you an example of what I'm talking about. Okay, so let's say we have an equation like this. If it is possible to isolate the square, then a square root is a good method to use. We'll talk about in a little bit how do you tell the difference. Okay, but this one is a good one. So when I say isolate the square, I mean get the squared part of the equation by itself. So if that's my goal, what should I do first? All right, add the 31. And what is 49 plus 31? 80. Okay. Have I completely isolated the square yet? Not yet. What I still have to do? Divide by 4. Okay. So divide each side by 4 equals 20. Okay. Now I have something squared equals something. This is what you're going for. Because if I have something squared on one side, I have something in my bag of tricks that can get rid of that. A square root. So if we square root both sides, remember if you do it to one side, you have to do it to the other side too. So So we square root both sides. I can get rid of that thing. So x, so if you, sometimes I see people doing this to remind themselves what it is they're doing there. So then what is x?
4.472135955.
Or you could leave it as a square root, so it's a square root of 20.
Well, that's it.
Uh-huh. Now, here's something that you probably didn't think of. It is the square root of 20. However, it needs to be that. It needs to be plus or minus square root of 20.
But you can write plus or minus both ways.
You could technically do that. Now, I'm going to have you guys, though, with this stuff, leaving them as square roots. Okay? Because when you write it as a decimal, it's an imprecise answer. Because you're always, with square roots at least, you're always having to, you got to round it off somewhere. Because technically square roots go on forever. They're decimals. So if you write it as a decimal, it's a rounded answer. The square root of 20 is the square root of 20, period. It's an exact answer. Anyway, the plus or minus part of it, though, why do you suppose I did that? There are two x-intercepts, right? Okay. And even the algebra that we use to get here supports that idea. Okay. Think about going back to here. If I had this equation x equals plus or minus the square root of 20, what if it happened to be the negative square root of 20? I'd have to square both sides to go back, right? If it's negative square root of 20 and I square it, what do I get? If I'm squaring negative square root of 20, that means I'm multiplying it by itself. Right. Wouldn't it be positive 20? The square roots would cancel each other out, and the negatives would cancel each other out. It'd still be 20. So if I square root 20, or I'm sorry, if I square root both sides of that equation, that x could have been the negative square root of 20. It would still work. If I plugged in a negative square root of 20, it would still work. So I have to consider both cases. So really all you need to remember there, though, is whenever you square root both sides of an equation, the answer always has to have a plus or a minus. So just put the little plus minus symbol there and you're safe. Okay? So this would be our two solutions to that thing. Thank you, sir. All right. Now, just so you guys are aware, your textbook is going to simplify the square roots. Okay? That's not putting it into decimals. Okay? I think this is kind of funny that they call it simplifying square roots, because when you're done, it doesn't look very simple. But I'll show you what it is that they're doing. As far as I'm concerned, no. But if you're looking up your answers in the back of the textbook, you might think you're wrong when you're right. So, yep, exactly. You take the number and you try to break it into two that multiply where one of the two, or maybe both, depends. Usually it's just one of the two. Where one of the two is a perfect square, so you can actually take the square root of that part of it. So what is the square root of 4? 2. So technically the square root of 20 is 2 square root of 5. So this answer in the back of your book would look like this. It would be plus or minus 2 square root 5. Okay? So just so you know, if you really want to check with what they have as an answer, you're going to have to simplify the square root. Okay? On a test or something, for me, I'm not going to worry about it. Okay? But just figured I should tell you that. All right, let's try another one of these guys. Remember, we're trying to isolate the squared part. So what if we had 4 times x plus 2 squared equals 24? Nope. Can't distribute into a square. If this little square was not there, absolutely. You got to divide by the 4. Yeah, because it's being multiplied, right? That left-hand side, the squared part of it is being multiplied by 4, so to undo that, we got to divide it over to the other side. So x plus 2 squared equals what? 6. Okay. So now I have x plus 2 squared equals 6. I have something squared, even though it's this x plus 2, equals something. So now this is my, yay, I'm ready to do this square root trick. Okay? So if we square root both sides right now, what are we going to get? If I square root this and I square root that. I just square rooted both sides. So when I square root a square, it canceled. So it's just x plus 2. Right? If I square root something squared, those two things cancel each other off, and it's just whatever else there was in there. It's just x plus 2. Hold your horses there, big guy. So x plus 2 equals then square root of 6, but what have I forgotten still?
Plus or minus thing.
Plus or minus, don't forget that. Always need to have it, no matter what. Okay, so now what do? I'm not quite done. Subtract the 2. All right, so I'm going to subtract 2, but I'm going to write the answer in a way that maybe you didn't think to do, and that's okay. But, again, this is how your book's going to do it. If you had plus or minus 6, then minus 2 after it, not wrong. It's fine. Okay? But the more accepted way to write stuff like this, they have a little plus or minus in the mix, is to put the number first and then the plus or minus whatever after it. Okay? Same thing though. Okay? So if you had it this way, I would not count that as wrong. Okay? Question?
So let's say it was x minus 2 equals plus or minus square root of 6.
Mm-hmm.
Would it be x equals 2 plus or minus 6?
Yep. Be positive 2 plus or minus square root of 6. Okay, so this would be what you'd see in your textbook probably. Square root of 6, though. Can we simplify square root of 6 down any? You could do 3 times 2, but are 3 or 2 perfect squares where you could square root them? No, so you just leave this one. You'd see it just like that. Wouldn't change. All right, so that's the square root method. Make sense? Think we can handle that? All right, so that's the sort of thing you're going to be doing with that, trying to isolate the part that's squared. Now, the next kind, you're not, I am excited. The next kind, you can't isolate the squared part. Yep. They look maybe something like this. Now you might be saying, yeah, I can, Mr. Herrick. I can take that 3x and move it over the other side, and then the x squared's by itself. Okay. Well, for this to work, x can't be on the right. Think about what would happen if x was on the right-hand side. You would have x equals something in terms of x. X needs to be a number, folks, not something with x in it, because then it's all just like wrapping around on itself and it's not really answering the question. So you can't have, if you're going to isolate a square, you can't have something with x over here because that's just going to give you an x in your answer, which doesn't work. Okay? So this doesn't work with the square root method because if you move that 3x to the other side, now you can't do the square root and it just falls apart. Okay? So we got to come up with something else that we can use. And factoring will work. Okay? So I'm going to leave this alone for, we're going to come back to this for just a second. Before we get into that, we need to talk a little bit about how factoring works. So I'm going to jump over to this side and do that. Factoring is, at least using factoring to solve this kind of stuff, is all based on this zero product property. And it's actually a pretty simple concept that you probably figured out when you were in elementary school. If a times b equals 0, let's say a and b are just two numbers. Okay? If a times b equals 0, the concept was probably elementary though. One of the two numbers has to be 0. Does that make sense? You can't multiply two non-zero numbers and hope to get 0. The only way to get 0 from a multiplication problem is to have one of the two numbers you're multiplying be 0 to start with. Still 0. Not necessarily, but we'll talk about that in a minute. But the zero product property basically just says this. If you have a product that equals 0, one of the two numbers, A or B, needs to be 0. Okay. Now, how do we apply that to this guy over here? Well, if we can break this thing into a multiplication problem rather than an addition, do you see how this one has a plus in it? So it's really the addition of two things right now. If we can turn this addition problem into a multiplication problem, then we can use this. Because look, it's equal to 0. That's what we're doing with these, right? We want to make them see. We want to see what is x that makes it 0. So the zero product property will help us as long as we have a product, though, a multiplication. So the way to turn an addition or subtraction problem into a multiplication problem is to factor the thing. Okay, and this is something you guys did in Algebra 1 a lot, but it's been a while. So I'm going to refresh you guys here a little bit with it. So the easiest way to factor is to look for what's called a GCF. Whatever, greatest common factor is what that is. Okay, so we look at both these two terms. It could be a number, could be a variable, could be a combination of numbers and variables, something that is common to both. So in this one, what's common to both? X. Okay, so we take out the GCF, and then we need to come up with, okay, if we were to pull that out of both of those two things, what would be left over? Well, this was x squared, so what's left over from that if I take an x out of it? It's the other x, right? Because x times x is x squared, right? Plus 3. Okay, do you see the multiplication now? It's right here. Okay, so my A in this case is x, and my B is x plus 3. Those are the two things I'm multiplying together. Okay, so what that means is x equals 0 or x plus 3 would be the one that had to equal 0.
So it'd be -3?
Uh-huh. So this right here is just like a nice little simple algebra problem to solve. Subtract 3 to each side. So x equals -3. And this one's already done, right? So your two solutions, 0 and -3. If you were to graph this thing, there's where your intercepts would be, 0 and -3. Yeah?
So you can only factor when it equals 0.
Yeah. Yeah, you can only factor when it equals 0. Yep, exactly. Okay, so this is one way of factoring, is this whole GCF idea, okay? Another way to factor that you guys learned about, that we need to probably brush up on, is what if there is no GCF? So ones that would look something like this. X squared minus 4x plus 3. Okay, there's nothing common to all three, right? This time I have 3 terms instead of 2. There is nothing that is common to all 3 of them. Okay, other than 1. But if you think about it, if I factor out a 1, what changes? Nothing, right? So factoring out a 1 doesn't really help me. So I got to think, okay, other than 1, is there anything else that I can take out? And there's not. You can't take a 3 out because 3 doesn't go into x squared and it doesn't go into 4x.
I mean, like, can you move it over the...
Oh, but then it's not equal to 0 and I can't do this zero product thing anymore. So I got to leave it all on that one side, but now I'm stuck where I can't do a GCF. But thankfully there's another way to factor. Okay? And the other way to factor has to do with these two numbers.
4 divided by 3, that's what you gotta do.
Nope. Just hold on. You'll remember it. It'll just take a second. You've done a lot of this, but it's been a while again. You're looking for two numbers that have to add together to give you the one in the middle, but multiply together to give you the one on the end. What two numbers add up to -4, but multiply together to give you 3?
-2.
You're close. Nope.
Or -1.
Nope.
What? How would -1 and 4 not work? -1 and -3.
There it is. -1 and -3. -1 plus -3 is -4. -1 times -3 is +3. Okay? Adds to this, multiplies to that.
So how does -1 and +4 not work?
Why does -1 and -4 not work? Because it doesn't add up. Yeah. So those two numbers that you come up with, they make your two factors. X minus 3, X minus 1. And again, we got a product, right? X minus 3 times X minus 1. So each one of those products could be the thing that's making it 0. So X minus 3 equals 0, or X minus 1 equals 0.
So then we got a 3 and then a 1.
We got a 3 and a 1.
So easy.
My mind is destroyed right now.
Do you guys remember when we talked about intercept form? It looked like this. It looked like that. Take a look at this. What if I just put like a 1 right here? Is that not the same thing?
The exact same thing.
Yeah, it's the same thing. Where are the intercepts on this thing?
3 and 1.
3 and 1, because we said the P and the Q are the intercepts, right? Right? Those are your solutions. I know, right? We just made a connection. 3 and 1, right? It's the same thing. We said X intercepts are the same thing as the solutions, right? Boom! There you go. It all fits. It's all the same stuff, okay?
One section. Can we have 2 sections?
No. Just one is fine. All right, so three different methods that we talked about, just to bring it back here real quick. The graphing, okay? On your calculator, look for those intercepts. The using a square root or factoring, okay? Using a square root, you got to isolate the square root both sides. Don't forget the little plus or minus. And then factoring, you factor it out. Use the zero product property to get your solutions. Question.
Why can't we just graph all of them?
Oh, you stole my question. So my next question was, couldn't we just graph these and find these solutions?
Heck yeah, we could.
Yeah, right? We could just put them in the calculator and graph them. Now, here's the thing. Your test that I'm going to give you is going to have a calculator portion and a non-calculator portion to it. Yeah. Now, the reason that I'm doing that is because there's more to this than simply arriving at an answer, okay? There are more things that build on this in the future. I teach pre-calc, all right? And we use roots of quadratics. We use roots of all kinds of different functions, like bigger polynomials and things. And this idea is crucial for being able to do those higher order ones later. And if you just plug everything into a calculator and find intercepts, you'd have no clue what's going on when you get to that point. Okay, so to make sure that there's a proper foundation there for that math that's coming later, if you take a college math course, you're going to have to do that stuff too. So most of you, this is important for future endeavors. So we need to still make sure you can do it without a calculator. Okay, so that's why I'm doing that. I'm not doing that just to be a jerk. Okay, I get it, but you know. Anyway, so before I set you loose on homework, though, I just wanted to be sure that you guys recognize something. There are 3 words that you're going to see in your assignment, and they all mean the same thing.
Root, solution, and zeros.
Roots, solutions, and zeros. We've been pretty much just calling them solutions through all of this. Okay? But roots, that's another term. That's one that more refers to x-intercepts specifically. Solutions is more like solving an equation. And zeros, well, that's more graphical too. You think about it because that's where y equals 0. Roots, think about a root of a tree. It's where it meets the ground. So x-intercepts, kind of where it meets the ground as the x-axis, kind of where it holds onto it. So, but it all means the same thing. So I just didn't want you to get thrown off by that. Okay? Just know that. So, all right. That's all I got. The rest of the time is yours to work on some homework, guys.
Do the homework.